Okay, let me start with a refreshment from last week's lecture. Where is it? Okay, maybe I can start here. Right. So last week we discussed about crystal structure, and the crystal structure it might be FCC, face-centered cubic, or body-centered cubic, or hexagonal closed package, and then I have been also demonstrated how to calculate and then what is uh, the topics and also the parameters in each strict crystal structure. Usually the one that we really calculate is actually the atomic packing factor, and also the coordination number, the number of the nearest neighboring and touching atoms, and the number of atoms per unit cell. Okay, and then there's also body-centered cubic and hexagonal closed pack. Right. So today, and then we also learn about crystallographic points, direction, and also planes. Yeah, this one here. Now I think we haven't. Okay, so this one now today let's talk about the crystallographic plane. So the previous one, just to refresh a little bit, the crystallographic points is the point coordinates. The way you read it is actually looks like if you want to read in Cartesian diagram. Okay, there is a Q, for example, this point tells you the lattice position reference to the x-axis, the lattice position reference to the y-axis, and then the lattice position with reference to the z-axis. Okay, and then the second one is crystallographic direction. So this looks like a vector where you want to find the position in the x-axis, which is u, to the y-axis, and also to the w-axis. Okay, and let's have a look. This is an example. So for example, here determine the direction for accompanying figure. This is the first one, that this is the end of the vector. So the first one you need to do is you have to notify which one is the end point and also the initial points. Okay, if you look at the endpoints here, you see that the x with the reference to the x-axis is actually 0. Okay, and the y which reference to the y-axis, you can project it to here, and it's actually b. The length is b. Okay, b, or 1 multiplied with b. And then z, we have to find the position with reference to the z-axis, which is the length of c divided by 2. So c divided by 2. Okay. With that sense, you can also try to find these points, where these points from the position, the x1 is a, and the y1 is 0 multiplied with b, because the reference with y-axis is here in the 0, and also z1 is also 0 with respect to the z-axis. Okay, once you got that one here, you get the tail coordinates and the head coordinates. The next one is to find your x2 minus x1, y2 minus y1, and z2 minus z1, and then here for example minus a, b, and c over 2. Okay, and the next one after that, we divide them with the respecting letter, the a, b, and c, and it will become, so we divide it, we put it into the formula where n is integer. Integer means if we have the over here is a pecahan, yeah, or a fraction, then we can multiply it with numbers to make it integer. Okay, in this case, for example, here, because there is a fraction here, c over 2 divided by c is equal to half. This one should be half, so then the integer is 2. So we multiply all of them. U, V, and W is actually become multiply with 2. Then we can get the U is minus 2, V is 2, and W is 1. Okay, and this is the enclosure where is negative 2, 2, and 2, and usually the indices put it in brackets, and we write the negative on the top, so negative 2, 2, 1. Okay, so so you can have a look at the procedure. So first you need to find the head coordinate first, and then the tail coordinates of the vector, and then after that check the coordinate differences by subtracting the the head coordinates with the tail coordinates, and after that you get the value of U, V, and W by putting the integer, and then the enclosure you will end up with the direction. Okay, so maybe hopefully tomorrow I can give you some maybe quiz, or not quiz, yeah, or maybe assignments for you to try to do it by yourself with another examples. Okay, another one is called crystallographic planes, bidang crystallography. In crystallographic plane is actually the orientation of planes of a crystal structure, and this is represented by the Miller indices, or with in bracket like this, and then HKL, where H is equal to the length of A divided by A, or this is the intercept of x-axis. Okay, and K is actually an integer multiplied with B divided by the intercept of the y-axis, and this one also L is the C multiplied with integer divided by C, where the C is intercept of z-axis. Okay, so in figure this one, the 3.11, it shows you the representation of series. For example, this is called 0, 1, 0, 1. Why? Because if you look at here, if this is the reference points 0, the plane has the intersection with the axis. Okay, because the plane has intersection with z-axis, so that means would pass the this one become your C become C as well. Okay, so that become 1 and 3. Okay, maybe I think I can try to write it using a tab. Give me a second. Let me close this one so I can check, because I need to log in with for the tab so I can write things up. Right, so this one, wait, this 2, 4, 5. Okay, so let me stop screen in here and share. Yeah, right. Okay, So here, yeah, you can actually try to see, okay, so if to make this one 0, 0, 1, you can try to put the numbers in here. So the h would be an intercept multiplied with a divided by a, whereas a is actually the intercept of x in this plane. Okay, now the question is this do you have any intercept in this is this plane has intercept with x-axis? What do you think? Do we have intercept with x-axis for this plane? If you think about it, this plane is actually parallel to the x-axis. If you have something parallel, yeah, if you have something parallel like this, oops, yeah, if you have something parallel like this for quite a long time, okay, it won't have it will have an intersection. Itu tidak akan pernah berpapasan. Okay, so that means the a, which is the intercept of to the x-axis, we can write this would be equal to infinity. Okay, so because it is parallel lines, yeah, this one and with the x-axis is parallel, so a actually it can be the intercept with the x-axis would be at infinity, or we can write it n multiplied with a divided by infinity, which is a number if divided by infinity is actually equal to 0. Okay, so that's why the h is equal to 0 here. Okay, that's also similar with k, yeah, which is k is actually the integer multiplied with b divided by the intercept with y-axis. B is for y-axis, and if you look at here, the plane also parallel to the y-axis. Because the plane is parallel to the y-axis, then it will have an intercept maybe at somewhere in infinity. So we can write it as infinity, that become also 0. Okay, and for L, it's actually an integer divided by a, multiply with a divided by c, which is the intercept with the z-axis. If you look at here, this is a 0, and then this is the plane, and the plane is intersect with this z-axis around here, and this become actually the length of the cube. Yeah, it is the length of the cube. So you can write that this is the intercept would be at c, at also small c. Yeah. Oh no, not L. Yeah, it should be sorry, it should be this one. Where is it? Wait. Give me 2 seconds. Okay. Okay, anyway, wait, discard, and then let's try it again. Okay, so I think I need just to write it down. So from h is actually, we call it n multiplied with a divided by infinity, that's become 0. The k also n multiplied with b divided by infinity, become 0 as well. And the last one, L, is n multiplied with c divided by the intersect with the z-axis, which is c, yeah, c, so it's equal to n. Okay, so this is called 0, 0, 0, 0, n, and then the n we can make the integer as 1, so then we can write it is actually 0, 0, 1. Okay, so then we can write this as 0, 0, 1. Okay, and the plane that is parallel to this plane, we can also say this is 0, 0, 1. Okay, maybe here is actually 0, 0, minus 1, but we can also write this is equal 0, 0, 1. Okay, we can also try the last one. Maybe you can see it on the yellow ones here. So here it is looks much better here. I think. Okay, for example, here around here you have 3 intersection. Okay, so you can see in the 0, 1 there. So you can find the h would be n multiplied with the intersection with the x-axis, which is this one. Yeah, which is the also the length is a because that's the unit cell. Yeah, with the this one a. So n. And then L also the same. We can here we can see that there is an intersection with the z axis. Sorry, with the y axis. So and b multiply with b, and then this also for the k is also similar with the divide by c is equal to n. So and then let's make integer as 1. So then we can get the plane would be 1, 1, 1. Right? So that is the crystallographic plane. Okay, I think let me give you another example, or let's try it. Maybe okay. Let's try, for example, this one, and then with maybe different color, and then this is the unit cube. Okay, and then my question is, so this is y, this is x, this is z. Can you try about maybe how about this one? If I put it, the one is in here, okay, and then the second one is here, and the third one is here, and then I make some plane. Can you all try? What is the crystallographic plane for this case? Okay, now the question is, if it pass this case, what you can do is you can actually add the additional cube there, maybe like that, and then try to find because the intercept would be with, that should be with x, y, and z. That means you have to try to find the intercept for the z-axis with the the vertical one that should be with the z-axis. Okay, so have a look, try it by yourself. What happens if we have this one? Let me just draw it from the beginning. For example, okay, if it is from half of here and there like that, for example. So this one, the z is actually, it's not in the z axis, yeah, the intersection. So we have to try to find which one goes to the z axis. Then you can find the numbers. The hint for this type of plane, it would be, there would be something that negative. The z should be negative. Okay, another one. Let's see, for example, wait. Let's see another one. For example, the for the plane, yeah. Let's an example about the crystallographic plane. Here, for example, this is the question is the construct 101 plane with the following unit cell. So for 101 plane with the unit cell, this tells you that it should have intersection with x-axis, this one, and it should have intersection with z-axis, this one, okay, and it should have a parallel with the y-axis, and this is the y-axis. So this plane is actually parallel to the y-axis. Okay, so here, if you can read the explanation in the example, this 101 plane intersect x-axis at A, this one, and then it parallel to the y-axis because B is infinity, and then it intersect with z-axis at C. So, and then you can try to construct the crystallographic plane. All right. Okay. Let's see the next one. Okay. Anyway, from so I think tomorrow I will give you assignments for you to try to do the calculation, and then let's continue about this one, the crystalline and non-crystalline materials. Right. So it's actually the crystal, the model or the crystal model that we learned before is actually it's called single crystal. Yeah. So single crystal is a crystalline solid that is in periodic and repeated arrangement of atoms, and it is perfect to extend throughout the entire specimen without interruption. So if you want a single crystal, so that means the crystalline solid should be periodic, and then in 3 dimension, all of them it should be extend and then throughout entirely without any interruption. However, the one that we see every day is actually we call it polycrystalline materials, because the most crystalline solid, for example, the this one, yeah, the tumblers or your aluminum laptop, and all of them, most crystalline solids and crystalline metals usually compose of collection of many crystal or grains. Why does it happen? It happens because when we make metals, it started with the melt, and the melt would be like this. So this is the yellow one is the melt, lelehan. And then when we cool it down, the first one is we call it crystallization. Okay, in the first crystallization, that would be we call it nucleus and or some seeds. Yeah, the nucleus. There would be a nucleation, right? And then there's nucleation and nucleation of one crystal. And after that, as we cool it down, or we just wait at a lower temperature than the melting points, the next step after a while, then the crystal will grow. Okay, these sides will grow to that sides, with this orientation will grow to that sides, this orientation will grow to that side, and so on, until the crystallization is complete. And if we look at under microscope, if you have a piece of metal, and then if we have some time to go to the electron microscope, we put it under the microscope, you can see that at the micrometer scale, that would be we call it grain boundary, batas butir. Okay, so the grain boundary is atomic mismatch within the region where the 2 grains meet, and then with this various solid stage of specification. Okay, and then you also need to know the concept of anisotropy. The anisotropy is actually in some cases the properties of things or the material, sometimes it a function of direction. Okay, usually in polymers or in ceramic or in fibers, they have different properties, yeah, with the different direction. Why? Because it is related to its crystal substance. Okay, so the physical properties of a single crystal in some substances depend on the crystallographic direction in which multi-measurements are taken. Okay, so if you have a single crystal, you have a type some atom arrangement, the properties, physical properties in this way and maybe in other way, that would be different. However, in if in polycrystalline material, or in a metal that we have in polycrystalline material, we call the properties is often isotropic, yeah, or we called it the substance in which measured properties would be independent with the direction of measurement. This is because in metals, because it contains so many grains, like in the previous one here, yeah, this one, because it has so many grains over here, so each direction will have a complement with each other, so they will have isotropic properties, or the properties would be similar in any direction. Okay, so here for example, in metal, we know that the tensile strength is the same, or the ductility is all the same in any direction. But however, in some other places, for example in fiber, if you have polymer or composite, there should be some anisotropy. Okay, and another one is called non-crystalline solid, which is actually called the lack of systematic and regular arrangement. So this is a concept of a non-crystalline solid. So this is crystalline because all of the ring has similar ring there, but over here they have a different ring. Yeah. Okay, so that is the first. This is the end of the crystal structure, and then let's continue to the next slides. That is about defect. About the imperfection. Okay, right. Okay, so let's so once we know about the crystal structure, we know the type of the crystal structure, we know the atomic packing factor, we know the what else, the density calculation, and then we know also about the concept of polycrystalline. Now let's talk about the imperfection. So yeah, so it has been assumed that the perfect order exists throughout a crystalline material on atomic scale, but the ideal solid is actually doesn't exist. Yeah, like I explained before, when we want to make a metal from the solid, from the liquid, the melting of metals, when we cool it down, that would be a process of nucleation and then growth, and then that will give you the polycrystalline one. Okay, and then of course it and also there are also a large number of defects, cacat, yeah, and it's called imperfection. Okay, and as a matter of fact, many of the properties of materials are profoundly sensitive to the deviation from crystalline perfection, and then the influence is not always at first, and often a specific characteristic or durability fashioned by the introduction of controlled amount or number particular defect. Okay, so what is a crystalline defect? A crystalline defect is the lattice irregularity, that which is one of them having more on the dimension on the order of atomic diameter. Okay, another crystalline defect, for example, we add some impurities in there, so that would be a crystalline defect, and then the crystal is not perfect. Okay, there are several types of defect. The first one is called a point defect. Okay, so the point defect would be associated with one or two atomic position. For example, one atomic can be vacant, hilang, kosong, the vacancy, or it can be linear, cacat garis, cacat linear, or which is one-dimensional, or interfacial defect or boundary, which are two-dimensional. Okay, and then impurities also discussed. Right. Okay. To watch the this one to explain about the point defect, let's watch a video that I prepared in the, I think I also have uploaded into EduNext regarding the point defect. So give me 1 minute there. Should be in my Dropbox. So, okay, so I think should be in. Okay, so let's watch. There are two types, point defect and let's watch this one about point defect. Let's watch this video first.
And now that we see that the fraction of vacant sites increase exponentially by the Arrhenius relationship as we go to higher temperatures, it's important to appreciate that it's the vacancy motion that makes atomic motion possible. What we'd emphasized when we first talked about point defects, specifically vacancies, that these are going to be an important part of our understanding of a very practical material parameter in a subsequent lesson, and so here we are. We're now talking about how point defects facilitate solid-state diffusion. And specifically, those individual vacancies, as illustrated here, and we can just give ourselves a quick review of the concepts from crystallography. What we see here is that familiar face-centered cubic pattern that we saw in the unit cell of aluminum back in that discussion of crystallography, and that face of the unit cell. This would be a 100 plane. Again, that front face of the unit cell. And so if one of those atoms is missing, one of these vacancies that's been produced by thermal agitation, thermal activation by bringing the material to increasingly high temperatures, now that provides a place for one of the adjacent atoms to move into and thereby provide atomic migration. Atomic migration by itself, without those vacancies, is always going to be very difficult. This is a very tight structure that we see here. And it's not at all easy for one of these atoms to squeeze through this very tight structure. Again, recall that 74% of the unit cell volume was occupied by atoms. That was the atomic packing factor for aluminum, for face-centered cubic aluminum, any face-centered cubic metal. And so now this vacancy is an enormous increase in local volume to allow this atom then to hop into that position and thereby provide one single step in the overall solid-state migration of atoms through this material. This sketch also indicates that vacancy migration then is by definition, and because of this one-to-one correspondence with the atomic motion, that vacancy has then moved obviously from this position up to that position in a complementary way. So this is an important concept to keep in mind as we continue to look at the large-scale result of this atomic migration as various solids are able to migrate and diffuse into adjacent solids.
Okay. Yeah. So that is about the vacancy. So what is vacancy? Right. So vacancy, kekosongan, is a very it's the simplest point defect. Okay. So the simplest of point defect, cacat titik. Okay, so it's called the vacant lattice sites, and it's actually one normally occupied, but when an atom is missing. So for example, in here, this is for example for the face-centered cubic for 100 crystal, like the professor said, and this is vacancy. Okay, and then in this this is called a vacancy, and the number of the total atomic sites that are required to formation of vacancy is actually quite a lot. Okay, and then the equilibrium number is actually a function of energy required, and then divided by temperature. So it is, we call it Arrhenius relationship. Yeah, the Arrhenius relationship that you also see it in the kinetics of chemical reaction. Okay, and then the second part also it can be a self-interstitial. Even the self-interstitial, if there is a room or this vacant here, or I think it's actually not it is uncommon, because here you have you can see that this ball should, or this atom should pass or berdesak-desakan, yeah, to see this this one there. Okay, so it's called a self-interstitial, where the atom from the crystal is crowded into an interstitial site. Okay, so there is a vacancy and also interstitial, and vacancy is actually function of temperature. As you can if you have a higher temperature, usually it would be that would be quite hard as again the vacancy. Okay, so and then in solids, okay, so here for example, sometimes it's we also always have impurities in solid. Okay, for example, okay, I want to make a silicone with 99.9999%. Okay, and at this level, 99.99999%, the order of the purity is actually, you know, the order of 10 to the 22 or 10 to the 23 of impurity atoms would be present in 1 cubic meter of material. So you can imagine that even the purity of 99.9999%, the impurity atoms is in the level of this high. Okay, so but most familiar material is actually not pure, or we actually sengaja, yeah, we actually purposely try to make impurities in solid, and the impurities in solid is called alloys. And these alloys, the impurities in solid, that is also called point defects. Yeah. And then in alloys, which is the impurity atom is actually added intentionally to impart specific characteristic of the material. For example, we actually add nickel and chrome to steel in order to increase the corrosion resistance as well as to improve mechanical strength. Yeah, so that is purposely added. Okay, and then here in the impurities also they will make it can be made a solid solution. It looks like a liquid solution, but it is in solid, so it's called a solid solution. Or a second phase, it depends. Okay. And then in regards to alloys, the solute and solvent is also term that commonly employed. The solute is the small substances, and the solvent is the larger part. Okay. Okay, so this is what looks like as a solid solution. If in the previous slide we use self-interstitial, but it is unlikely because you have to crowd one atom into the vacancy here. But what we can do is actually we can put interstitial impurity atom. Okay, so what is interstitial atom? In interstitial atom, the impurity atoms fill the voids or interstices among the host atom. Okay, the very common interstitial atom is, for example, we want to make iron or iron and steel, where the iron is actually, it has impurity of carbon. Carbon atom has a very smaller radius compared to iron. So for example, this is the carbon atom in iron. Okay, so the carbon atom fill the voids or the interstices among the host atom. Okay, is it doable? Is it of course doable because the carbon has a smaller radius there. Okay. Another one is called substitutional impurity atom. So if we have another metal, we have another atom that has a similar characteristic to the host atom, for example, the similar radius, similar electronegativity, similar density or something. So we can put one atom from different part, yeah, or maybe different metal to here as a substitutional impurity atom. Okay, so for substitutional type, the solute or impurity atoms replace or substitute for the host atom. Okay, there are rules. We call it Hume-Rotary rule for substitutional solid solution. The first one is atomic size factor, which is should be the two atoms should be less than 15%. Maybe I'm going back to here. The very common substitutional alloy or atom is between copper and nickel. Both copper and nickel have quite similar radius and also the electronegativity as well. So the copper and nickel, they can make a substitutional impurity atom. And then the second one after the size factor, the radii, so where the difference of atomic radii should be less than 15%. The second one is the crystal structure. For appreciable solid solubility, the crystal structure for metals of both atoms must be the same. Okay, and the third one is the electronegativity factor, where the more elements and more electronegative to the others, that would be the great likelihood that they will form an intermetallic compared to substitutional solid solution. So they should have quite similar electronegative or electropositive properties. And then the valencies, other factors being equal, a metal who has more tendency to dissolve to another metal, higher valency than dissolve in one valency. Okay, so this is an example of formation of interstitial solid solution. For example, this is FCC. So you can see here actually the FCC here, we can get the octahedral, the part which is the empty over here, 0, half, and 1. They can try to snuck into that voids, and this one they can also snuck into this void. Okay, so for example, for both FCC and BCC crystal structure, there are two types of interstitial site, tetrahedral and octahedral. And then because of metallic materials have a relatively high atomic packing factor, which means that this interstitial position are relatively small, and then the atomic diameter of the interstitial impurity must be substantially smaller than the host atom. Okay, so this is a very quite common examples is this is the Fe atoms, and this is the carbon atom. Okay, I think yeah, so this tells you about the point defect. So to sum up, the point defect can be divided into self-interstitial, here, self-interstitial, and then vacancy, okay, in for from the atom from the crystal. And then for alloys, there are two types of solid solution. The first one is interstitial, where a small atom snuck into the void, and the second one is substitutional impurity atom. Okay, tomorrow we're gonna continue with a line defect or dislocation, and then there's also some video as well to let us understand about this concept. All right, everyone, looks like the 1 hour is almost up, so thank you for listening. And then usually I put the recording during the weekend, and then tomorrow there would be assignments regarding this type of equations, and also some calculation for you to understand the concept more. All right, thank you very much, and I'll see you again tomorrow. Bye bye.
Thank you very much, ma'am.
Thank you, ma'am.
Thank you, ma'am.
Thank you so much.